Welcome everybody to another lecture video. In this chapter, we're going to be looking at aldehydes and ketones. So let's just jump right in. So aldehydes and ketones contain carbonyl groups. And so one of the learning objectives in this chapter is going to be, or in this section, is going to be identifying the carbonyl groups and then determining if it's an aldehyde or a ketone based on what's attached to the carbonyl. Carbonyl is this C double bond O. Now, we're going to be writing IUPAC names and common names for aldehydes and ketones and drawing their structures and line angle formulas. So I'm showing you here formaldehyde. The IUPAC name would be methanal because it has one carbon, and aldehydes get the Al ending. And this is actually, this solution here is called formalin. It's an aqueous solution that's only about 40% formaldehyde, but formaldehyde is used as a germicide, and it's also used to preserve biological samples. You maybe have heard of formaldehyde before, or maybe you've smelled it. So the carbonyl group in the aldehyde and in the ketone is that C double bond O. Now, the aldehyde has at least one hydrogen atom, whereas a ketone is actually bonded to multiple carbon atoms. So you can see that here aldehyde has one H, where ketones do not have H's. An aldehyde can have two H's, like we saw here, but it has to have at least one. So aldehydes and ketones with that carbonyl group end up being at about 120-degree bond angle. So these are trigonal planar, so this is a flat sort of group. And yeah, there is the aldehyde and ketone. So ketones are carbonyls with carbons on them. Aldehyde is a carbonyl with a hydrogen, at least one hydrogen. Now the carbonyl group is very polar. The oxygen atom has two lone pairs, and it's much more electronegative than the carbon. The carbonyl group then has a strong dipole, with the partial negative charge being towards the oxygen and the partial positive charge being on the carbon. And so the polarity of the carbonyl group will strongly influence the physical properties like the melting point and boiling point, vapor pressure, solubility, and such. That's not how you spell solubility. Of the aldehydes and the ketones. So that carbonyl group is going to contribute. In the IUPAC system, I mentioned before, aldehydes are going to get the Al ending. We don't need to number anything for the aldehyde or specify a number because it's always on the end of a chain and it'll always be the number 1. And then with 4 to 5 carbons, or 1 to 4 carbons, sorry, less than 5 carbons, we can use common names, which will end in the word aldehyde. Show you some examples here. So we've got a 1 carbon molecule that would be methane, so methanal. We've got a 2 carbon compound, ethane, so ethanal. We've got a 3 carbon compound, so propane or propanal, and butanal. Now the common names for 1 through 4 carbons are form, acete, propion, and butyr. So if you ever hear butyraldehyde or propionaldehyde, or what's the other time when we use these? There's other times when we use these as well. It isn't just for aldehydes, but I'm kind of spacing on it. Ketones, I guess, as well. You may have heard of acetone. Acetone is using that common name acete. It should be I guess it would be. Actually, I'm not sure that you can actually have a 2 carbon. I was going to say this is the 2 carbon ketone. You have to have 3 carbons to have a ketone. So acetone should really be called propanone. So yeah, I don't know why I'm telling you this because it's just going to look weird. It doesn't follow the trend. And I actually don't know how to explain why that's the case. We call this acetone, but it has 3 carbons. Yeah, it doesn't make sense. I don't like using these common names. We're going to stick to IUPAC names. So methanal, ethanal, propanal, And when we get to ketones, we'll use common names. If we don't use, we'll use common names, but not the common names from these. There's a different common naming mechanism that we'll use. Here we have a benzene, and when a benzene has an aldehyde group on it, we can call it benzaldehyde. Benzenal would also work. Benzenal. All right, quick learning check. So this is a aldehyde. Well, it says it's an aldehyde. You can also tell because it has an H on it. So go ahead and name this. Again, the ending just gets an AL ending. We still have to number from the aldehyde to get to our substituent. And then we name just like we would name with substituents and all that. So pause it, give it a shot. Hopefully you came up with pentanal and then 3-methylpentanal. Pentanal because there's 5 carbons, Al because it's an aldehyde. Alright, ketones. When we name ketones, we use common names and not the common names that we were just looking at. So those were common prefixes. These are common this is a common name for a ketone. So for example, let me draw acetone. So we have CH3, C double bond O, CH3. So this has 3 carbons, so it should be prop. We want to call this propanone. Propanone. I don't think I have it mentioned here that we add the O-N-E endings. But we are. I think it's on this next slide, actually. Maybe it's not even on the next slide. So I guess I have to say it now. When we name the ketones, we replace the E with O-N-E. And then the chains of the 5 carbon, or the chains of the carbons are numbered from the side that has the carbonyl closest to it. But we'll get to that with some bigger examples. Here, let's look at this 3 carbon compound. So this is propanone instead of propane, propanone. We don't have to say where the ketone is because it could only be on the number 2 carbon. We wouldn't have to say, for example, 1-propanone or 2-propanone. We couldn't have a 1-propanone. It would be a propanal if that was the case. And I challenge you to draw that so you can see that for yourself. Now the common name here is acetone, which doesn't make sense because we see that it should be called propianone. If anything, acetone should be for 2 carbons. So yeah. Now of course acetone wouldn't make sense anyways. If we tried to draw a ketone with only 2 carbons, it wouldn't work. So this is the simplest ketone we can get. Maybe that's why it has the acete, name in the beginning. Okay, the other way that we can name this is we can talk about the alkyl groups and then just say ketone. In this case, we have a methyl and a methyl. So dimethyl ketone. So that would be the common name. So common names here just have us naming the groups on either side of the carbonyl and then saying ketone. Let's try these. So propanone, aka acetone, we just looked at that. So now we look at this guy here. This is butane. This is actually butanone. And again, we don't have to say that this is the number 2 butanone, because even if it was on the number 3 carbon, we would have numbered the opposite direction. We would have said this is the number 2 anyways. So butanone just means 4 carbons with a ketone, but we could say that this is a methyl group and an ethyl group. So the common name would be ethyl-methyl ketone. Not methyl-ethyl, alphabetically, ethyl-methyl. 3-pentanone. Now we have a 5 carbon ketone. Now here we do need to specify that it's 3 because it could be 2, right? If we move the ketone to either the number 2 or the number 4 position, depending on which way we went, we would still always number it as number 2 because we would, whatever side gets to the ketone sooner. But what I'm saying is we could have a 2-pentanone and a 3-pentanone. Those are both possible for a 5 carbon ketone. 2-pentanone and 3-pentanone. We can't have a 1-pentanone because that would be an aldehyde. So here we have an ethyl group and an ethyl group, aka diethyl. Sorry about that. Diethyl ketone. We can even do something like this. If I just had a methyl group, this is 1, 2, 3, so that's a propyl group. It would be methyl propyl ketone. So, naming ketones using the common name, if we were naming this using the IUPAC name, then this would just be 2-pentanone. Okay. Cyclic ketones, we use the prefix cyclo, just like we do whenever we're talking about alkanes, cyclic alkanes. Any substituents that are located on the ring just get numbered, starting with the carbonyl carbon as number 1, and then the ring is numbered in the direction that just gives the lowest number to any substituents. So here we have cyclopentanone, because there's 5 carbons and it's a cyclic compound. Here we have 6 carbons, so it's hexanone. So cyclohexanone. Numbering 1, 2, 3 gets us to the methyl. Numbering 1, 2, 3, 4, 5 in the wrong direction also gets us to the methyl. So 5-methyl cyclohexanone or 3-methyl cyclohexanone. The 3 is better. All right, go ahead and give this one a shot. This is a ketone. If you want to name this one as the common ketone, realize that this group right here is a butyl, but it isn't a straight chain butyl. This is one of those isomers of butane. It might be a isobutyl or a sec-butyl or a tert-butyl. So if you're going to name it using common names, you got to consider that. All right, go ahead, pause it, give it a shot. Now, if you're naming this using the IUPAC system, then we're going to call this 1, 2, 3, 4, and 5. So this is 2-pentanone with a 4-methyl on it. 4-methyl to pentanone. Otherwise, this is isobutyl methyl ketone. Isobutyl methyl ketone. Okay. Four-methyl 2-pentanone, of course, being the IUPAC name. So, why am I showing you this? I guess this is formalin again. So formalin is that 40% formaldehyde solution. I mentioned it's a germicide. It preserves biological samples. It's also used in industry as a reactant in the synthesis of polymers that get used in fabrics, insulation materials, carpeting, pressed wood products like plywood, plastics for kitchen counters. So formalin's pretty big in industry. Exposure to fumes can irritate your eyes, your nose, upper respiratory tract. Skin rashes can cause if you get contact on your skin. There's headaches, dizziness, general fatigue. It's not a good compound to be around, aldehydes. Ketones as well. Simplest ketone, known as acetone or propanone. Colorless liquid. It's got a mild odor that has some wide use as a solvent in cleaning fluids, paints, nail polish remover, rubber cement. I mean, you probably know the taste or smell. Hopefully not the taste. In the body, acetone can actually be produced in uncontrolled diabetes, or if you're fasting, you form things called ketone bodies. The keto diet is what that's all about. Deprives your body of carbohydrates, and you start to break down fats and muscle for energy, and the fat breakdown results in these ketone bodies, which are ultimately acetone and formaldehyde or ethanaldehyde or ethanal. Yeah, so there's a little bit of a relationship to health there. Now, also in industry, Naturally occurring or aromatic aldehydes are used to flavor food and fragrances and perfumes and such. Benzaldehyde is found in almonds. Vanillin is found in vanilla or can simulate the vanilla taste. Vanillin simulates the actual vanilla beans. And cinnamonaldehyde is the compound that can imbue a cinnamon flavor to your product. So gums that have cinnamon flavor often will have cinnamonaldehyde in them. All right, quick learning check. Go ahead and identify these compounds as being either aldehydes or ketones. Uh, if you're unsure by the condensed structural formula, then draw it out and give carbon the right number of bonds so that you can see. All right, go ahead and pause it and give these a shot. Hopefully you came up with aldehyde. Actually, I can just do this. Bump. Aldehyde, ketone, ketone, aldehyde. CHO is aldehyde. COOH is carboxylic acid. Cylic acid. You'll see those occasionally as well. CO seems like carbon's missing some bonds, right? Must be because there's 2 to that oxygen. All right, another learning check. Name these. One of them is an aldehyde, one of them, actually both are aldehydes, so go ahead and give both of these a shot. Hopefully you came up with 4-chloropentanal for that first one, and 2-ethyl benzaldehyde for the second one. This is benzaldehyde. That's the number 1, so this will be the number 2, and it's ethyl. Another learning check. Give the IUPAC name of the following ketone. So this is a cyclic compound. So go ahead, pause it, give it a shot. So this one here is 5 carbons long, right? So cyclopentane, cyclopentanone, and then you have 2 options, 1, 2, 3, or 1, 2, 3, 4. So hopefully you choose this way when you're naming, and this becomes 3-ethyl cyclopentanone. I suppose you could say 1-cyclopentanone. It's unnecessary to say the 1. 3-ethyl cyclopentanone. This is the 1. All right. Name these as well. So lots of naming checks right now. So pause it, give these a shot. These are easy. These 2 aldehydes and a ketone. With the ketone, try using the common name as well. Name it with the common name. So we've got pentanal. Easy. We've got ethyl methyl ketone, or 2-butanone. And here we have, this one's a fun one. 1, 2, 3, 4. So it's butanal. 3,3-dimethyl, butanal. All right, let's transition to some physical properties. So aldehydes and ketones, again, have that polar carbonyl group. Partial negative charge on the oxygen, partial positive charge on the carbon. This is going to affect its properties. So let's describe the boiling points and the solubilities in this section. So at room temp, methanol, or formaldehyde, and ethanol are gases. So room temperature, carbons, 1 through 2 for our aldehydes. These things are gases. Aldehydes and ketones that have 3 to 10 carbons, they're liquids. And once we get into like the 20 carbons or so, they start to become solids. The polar carbonyl group with the negative charge and the positive charge on the carbon, has an influence on the boiling point and solubility because of the way that they interact with each other. So having those negatives and positives on neighboring molecules means that they have some bit of attraction to them. And the longer these chains get, the more other attractions there'll be. And that's why as we start to increase the number of carbons, it becomes harder and harder for our molecules to pull away from each other. That's the difference between gases and liquids. Gases have more energy and more motion. They can fly around without being stuck to each other. Liquids don't have that same sort of motion. They can move past each other, but they ultimately can't break free of each other, and that's due to these bonds. So when we start to compare aldehydes and ketones, we see that they both have these polar groups. The higher boiling points, aldehydes and ketones will have higher boiling points than alkanes and ethers of similar mass, because the alkanes and the ethers don't have carbonyl carbons. They don't have any polar groups in them. So when we're ranking from low BP to high, actually that's on my next slide. I can just show you that here. So again, higher boiling points than alkanes, but we'll see lower boiling points than alcohols, because alcohols actually can do hydrogen bonding. So H bonding gives the strongest sort of attraction, so that requires the highest temperatures for boiling. Only dispersion forces, so no hydrogen bonding, means that we don't have very many forces at all, and that doesn't require very high temperatures for boiling. But intermediately, we have the aldehydes and the ketones, because they are more polar than alkanes and ethers, but less polar than alcohols. Now, the ketones are actually more polar than the aldehydes, and the reason for that is because as the negative oxygen here, right, starts to pull electrons, the carbon starts to become positive, and then the carbon is also more electronegative than hydrogen. So in the aldehyde, some of hydrogen's electrons actually go towards the carbon, and so carbon is slightly less positive, and hydrogen is slightly more positive over here. But in the ketone, the carbon atoms have the same electronegativity, and so this carbon here in the middle isn't able to get any electrons from these carbons. And so the amount of positiveness is slightly greater than the amount of positiveness in the aldehyde, because the carbon in the aldehyde was able to pull some electrons from the hydrogen. What that basically means is the dipole of a ketone is slightly stronger than the dipole of an aldehyde. So that means, just like magnets, if you have stronger magnets, stronger forces required to pull them apart. So propanone, or ketones, all of the same size, considering you have the same number of carbons or the same rough molar mass, ketones will have a higher boiling point than aldehydes. You can see a trend here in the table as well, as you go from 1, 2, 3, 4, 5 carbons, 6 carbons, you start to see the boiling points also going up. And as far as the solubility, you see that that's inverse. So the smallest compounds will have the highest solubility, and actually once we get to 5 carbons or more, I think here 6 carbons, it becomes insoluble. So the polar group is good to help it dissolve in water. It's also good to help raise the boiling point. So here we're not actually comparing alkanes to aldehydes and ketones. Here you can see this is just aldehydes and ketones next to each other. So as this aldehyde and this aldehyde and this aldehyde get more and more carbons, you see the boiling point go up. All of these are soluble because they're aldehydes and ketones. Remember methanol, methane, ethane, propane, just the alkanes, those are not soluble in water from the get-go. But these are because they have that polar group. All right. Solubility of alcohols and of aldehydes and ketones. With 1 to 4 carbons, we're soluble. So just to reiterate, soluble. 1 to 4 carbons. 5 or more becomes slightly soluble, maybe, but 5 or more, let's just say, insoluble. I know with 5 it could be soluble, but it really depends on what the groups are. And the reason that these are soluble is because they form hydrogen bonds. And the hydrogen bonds that are forming are between the carbonyl groups and the oxygen-hydrogen bonds in water. These are also very polar. The oxygen is very partially negative, the hydrogen is very partially positive, and so the same reason. There's also an additional bit that the oxygens have lone pairs, and so those lone pairs are always trying to seek out positively charged nuclei, and so these hydrogens fit the bill. So that's what adds to the solubility. Now, an aldehyde is able to be soluble in water with the oxygen on the carbonyl group, and I guess that's it. The ketone as well. So they can both make the same number of hydrogen bonds. I guess I was getting ahead of myself. I'm imagining already when we get to the carboxylic acid, we're going to have another hydrogen bond ability here. But that's not here yet. So aldehydes and ketones. All right, quick learning check. Decide whether or not each of these would have, or which of the two the two compounds in each of these would have the higher boiling point, and then try to give an explanation for that. So pause it, try the pair in A, the pair for B, and the pair for C. Which one has the higher boiling point? So for A, the aldehyde has the lower boiling point than the alcohol. Alcohol can hydrogen bond, so it has a higher boiling point. For B, the ketone here has the higher boiling point because alkanes don't have any polar groups in them. For C, it was the ketone that has the higher boiling point because, again, the alkane doesn't have any polar groups. And for this learning check, for each of these compounds, decide whether or not it is soluble in water. Pause it, give it a shot. This should be easy. Now, hopefully you weren't tricked into thinking these were all aldehydes and ketones. The very first one is an alkane. So alkanes are not soluble, but alcohols, aldehydes, and ketones are all soluble provided they have less than 6 carbons. Good job. Let's talk about some of the reactions now for this chapter. So aldehydes and ketones can undergo, not all of them can oxidize, but they can all reduce. So they can all undergo reduction. Certain aldehydes can also, aldehydes can oxidize, ketones cannot, and we'll talk about that. The goal in this section is to draw the structural and line angle formulas for the reactants and products of these reactions. What I'm showing you here is called a Tollens test, or a silver mirror test. And the silver mirror, forming here on the inside of the test tube, forms when the oxidation of an aldehyde will reduce the silver ions in the solution into silver solid. So a Tollens test requires having some silver ions, but in the presence of an aldehyde, or I guess in this case, yeah, this is oxidation. So in the presence of an aldehyde, they'll gain an electron and actually deposit on the surface of glass. And so in this case, they'll deposit on the test tube. That's the positive indication that oxidation has occurred. But we'll look more at that in a second. So aldehydes oxidize readily to form carboxylic acids. Ketones, on the other hand, do not undergo oxidation. So what I'm showing you here is an aldehyde, and I'm showing you here is a ketone. So this is examples of what those formulas will look like. A ketones formula should have no product or no reaction written at the end because it can't oxidize. There's nowhere to increase a bond to O. But the aldehyde we can, and we've looked at this already in the alcohol chapter. Remember, we can decrease this bond to H and add a bond to O in there. That's what oxidation here means. So the aldehyde will oxidize into carboxylic acid. We're not going to worry about naming those just yet. Now the Tollens test is actually, it can be used to distinguish between an aldehyde and a ketone. So for example, if I have an aldehyde in a jar and I have a ketone in a jar, I should say beaker, in a beaker, and I don't know which is which, I can use the Tollens reagent, which is actually a silver solution. It's AgNO3, silver nitrate, and I can add this, actually I think ammonia as well, and I can add this to the solution and it will oxidize the aldehyde producing that mirror finish, but not the ketone. And so right then I'll be able to tell which is which. And that's actually something I think we do in lab. If not because it's expensive and because it uses silver, we use some other tests. But that's one of the ones we could do in lab. So again, it reduces the silver ion into silver solid. So that's what gives that silver sheen. Now, another way that we can sort of do a test like this to differentiate between an aldehyde and a ketone is something called a Benedict's test. Now, a Benedict's test gives a positive when we have a compound that has an aldehyde functional group next to a hydroxyl group. So, in fact, I've got an example of that right here. So these are sugars, and we're going to look at sugars in the next chapter. Notice that there's an aldehyde group right here. This is the carbonyl with an H, okay? Next to it, so on the carbon next to it, we have a hydroxyl. This is the situation that a Benedict's test is really good for. It's good for detecting sugars, for one, but here's a simpler one. Here we have the aldehyde group, and then on the carbon next to it, we have a hydroxyl. So what a Benedict's test does is that if you have that situation, aldehyde plus hydroxyl, then we can use the Benedict solution, which has copper ions. It's a copper 2 plus. It comes from the copper sulfate. And when we add this solution, if there's an aldehyde there and we heat this, then a brick red compound of copper oxide forms, copper 1 oxide. And so the solution will go from being blue, it's also blue because of the copper, to being red. And so this test is negative, usually negative, for simple aldehydes and ketones. So again, it's good at differentiating between aldehydes and ketones from those that have a hydroxyl group on them. We actually use this Benedict's test to determine if you have sugar, for example, or glucose in your urine. This is a test to tell if you've got, kidney damage or something, because you shouldn't have sugar or anything inside your urine. So this test will really quickly determine that. Yeah. And so glucose, the sugar that would be in our bodies, and the Benedict solution in the presence, if in your urine, if we added this together, it would turn red and we would know you've got sugar in there. So that's a real life way that we use this test. Now, aldehydes and ketones can be reduced. Remember, only aldehydes can be oxidized, but they can both be reduced. They get reduced either by using hydrogen gas or something called sodium borohydride, NaBH4. These are reducing agents, and they usually require a catalyst, something like platinum or nickel or palladium. And when aldehydes and ketones get reduced, they get reduced all the way to alcohols. And we do this by decreasing the number of carbon-oxygen bonds. So just like our alcohols in the alcohol chapter last got oxidized into aldehydes and ketones, now we have to undo that. So an aldehyde, right, will always turn into a primary alcohol, because that's what primary alcohols oxidize into, is aldehydes. And if you remember that, you might remember the secondary alcohols are what give rise to ketones. So basically we're undoing that here. So in an aldehyde where you had 2 bonds, we're going to remove one of those bonds to the O. So you can kind of think of it as, now we need to have, now this is just 1 bond and we need something else. And since we're adding H2, there's 2 places where H will go. One is to make oxygen happy. Oxygen wants to have 2 bonds. And the other to make carbon happy. Carbon wants to have 4 bonds. The same thing will be here on the ketone. We have 2 bonds that we're going to turn into 1 bond, which means we need to still have 2 bonds on carbon. We're adding 2 H's, so an H to each of these things. Both of these atoms had 2 bonds. They both still want to have 2 bonds. They both still do have 2 bonds. Practice these. Every molecule is different. Every aldehyde will always look like this on the end, but it's this part that's different with your aldehydes. Same thing with your ketone. Whatever's on your ketone, leave it on your ketone when you're done. All that's changing is the carbonyl. Only carbonyl changes. Okay, learning check. Write the condensed structural formula and name of the oxidized product when each of these is mixed with a Tollens reagent. So, assuming we're mixing these with the silver ions, draw and name the product that you get. So go ahead and pause these, give them a shot. Now, what's with butanal, we're going to change the, I guess I don't have to draw it, I can just show it to you. We're going to change the aldehyde group to the carboxylic acid group. We added another O. So we're increasing the bonds to O. You don't have to name this one. We haven't gone over names yet, so don't worry about that. But you might see that we add oic acid to the end. Acetaldehyde, or ethanal. This guy has 2 carbons. Again, we're turning that into a carboxylic group, and then oic acid is what we say. So ethane becomes ethanoic acid, but we'll name those later in that chapter. The last one, the ketone, you had to remember ketones can't oxidize. So nothing to draw, nothing to name. Another learning check. Predict the product for each of the following reactions. Okay. So here we have, we're adding hydrogen. So you should recognize that as a reduction, or reducing this. So right off the bat, this is an aldehyde, this is a ketone. So we should be drawing some kind of alcohols. And this one should be primary, this one should be secondary. So go ahead and give those a shot. Pause the video, try it. So your primary alcohol, right, still has this business on it. That shouldn't change. And now you're just adding 2 H's. Same thing with your cyclic compound. Here, picture that and that as just the parts of your ketone, right? So none of that's going to change. All we're doing is making this 1 bond. Carbon still wants to have a hydrogen attached there. We don't typically show those on line angle, but we do show the H that goes onto the oxygen. If you had shown this, you wouldn't be wrong. Sometimes putting that hydrogen on the homework makes it wrong because it's implied. You don't actually have to stick the hydrogen there. So if you entered something like this on the homework and it gave it to you wrong, it's just getting rid of your H. Since we're not showing all the H's over here, it's kind of inconsistent to just show 1 H randomly. So if we're not showing any H's, then don't show any H's. Alright, let's talk about the last part of this chapter that kind of transitions into the next chapter. And this is the addition of alcohols. So hemiacetals and acetals. So we can react, we can oxidize aldehydes and ketones, or I'm sorry, we can reduce aldehydes and ketones. We can oxidize aldehydes. We can also react both of these, aldehydes and ketones, with alcohols to form new compounds. So we're going to try that right now. I'm showing you here maltose. Maltose is a disaccharide, and it's actually produced from the hydrolysis of starch in grains such as barley. But in maltose, more particularly, what's important is that it has an acetal bond. An acetal bond linking 2 glucoses. So we're going to look at what acetals are. And later in the next chapter, we'll actually look at maltose more specifically. We'll look at carbohydrates. So our goal here is to draw the condensed structural and line angle formulas for the products of these acetal and hemiacetal formations. So first off, let's talk about what these are. When we add 1 alcohol to an aldehyde or ketone with an acid catalyst, we form something called a hemiacetal. So this is a hemi. Again, this comes from an aldehyde or ketone that gets added to an alcohol in the presence of some acid catalyst. We get a hemiacetal. A hemiacetal contains two functional groups on the same carbon. The carbon has a hydroxyl or an OH group, but it also has an OR group, where that R could be anything. It could be an H, it could be a CH3, it could be a bunch of, a big long chain of carbons. It could be a benzene, it could be a bunch of stuff. R just means something. Now, hemiacetals are usually unstable, and they'll react again with another alcohol. So our aldehyde and ketones reacted with an alcohol to give us a hemi. And now our hemi will react with another alcohol to produce an acetal. The acetal is a carbon that has two functional groups, or two, we call these alkoxies. This OR and OR, right? This could be OCH3, this could be OCH2CH3, right? Or any combination of those. This just means it's an oxygen with an alkane group, alkoxy. You might remember that a little bit from, I think we were naming alkoxy stuff earlier in the alcohol chapter. Maybe not. Maybe that's in the next chapter. I can't remember now where I just talked about this, but I feel like I just talked about this with somebody. Okay, so hemiacetals are one OR group. Acetals are two OR groups. Okay, and these come from the aldehydes and ketones. So let's see how that happens. So commercially, compounds that are acetals are used to produce vitamins, dyes, pharmaceuticals, perfumes. So they're pretty useful. To get to the acetals, we have to start with the aldehydes because they're often more reactive than ketones, and that's because the carbonyl carbon is more positive. And so, wait, aldehydes are more reactive than ketones because the carbonyl is more positive? I think it's saying that the ketones carbonyl is more positive. The aldehydes carbonyl is slightly less positive, but that makes them more reactive. In either case, the aldehydes are more reactive. The presence of the two alkyl groups in the ketones makes it difficult for the alcohol bond to form with the carbon of the carbonyl group. So that's why it's a little harder. What I'm saying is we're going to form a bond here to this carbon. This O is going to reach out and touch this carbon, which is going to cause this lone pair to come up here. That's why it's going to end up grabbing a hydrogen. That explains why we have a hydrogen on there. And then the rest of this molecule, the OCH3, will also be attached to that carbon, and that's why we see it there. With a ketone, the fact that this is a CH3 and this is a CH3 and not an H makes it a little harder for this to happen. So it does still happen, and especially when it's acid catalyzed. But now we're focusing on the aldehydes for now, because it happens easier. It's the same mechanism if we were to do this with a ketone. It just is easier with an aldehyde. So the first alcohol gets added on, and we're left with the O that used to be part of the carbonyl. I apologize for my screaming children. The O that's here, that's left behind from the carbonyl, gets the H, and that's why our hemi has an alcohol group and an OR group, because that carbonyl has a hydrogen on it. That's why it's a hemi. Once we add that second round of alcohol, and we could add a different alcohol, it doesn't have to be the same alcohol. Here we're adding the same one, and you can see what that ends up looking like. But we could add two different alcohols. It replaces the OH. This is going to come in here. This is going to come out. The OH here is going to come here, giving us the water. So the H's get shifted around a little bit, but we end up with two H's and an O as water, and then the alcohol. I'm sorry, not the alcohol, the OR group. Oh, I have to close this door. I'm sorry. So here is the hemiacetal and acetal formation shown again, this time with ketone. Wait, right? This is showing you the acetal formation. Oh, this is just showing it to you, showing both of them. So here is the the aldehyde going into the hemi, going into the acetal. Both of these exist in an equilibrium, meaning that the acetal can turn back into, if we leave it with water for too long, it can break back down into the alcohol and the hemi, which can also break back down into the alcohol and ethanol. And then here's the ketone, that we didn't really look at the ketone one. So here we're adding an ethoxy group. So that's going to get added to the carbon. And so here you can see it's been added. The oxygen becomes hydroxy, or an alcohol group. And then upon addition of the next round of alcohol, that second ethoxy gets added on, and the alcohol group removes an H and becomes a water. That H came from right there. So both of these are reversible, and they are forward directions as well. They always result in the same thing, a double substituted carbon. This carbon now has two groups on it, and the aldehyde still has the H, the ketone still has that other group. So nothing changes with that regard. It's just we're taking the opportunity to break the carbonyl into two separate groups, and then those two groups become those OR groups. This is important because this is how the monosaccharides in our next chapter are going to link together. Each one of our sugar compounds is going to be starting out as either an aldehyde or a ketone, and then it'll close on itself to form a ring. Actually, I'll show you that right now. Each one of our sugars is going to have aldehyde groups or ketone groups. They'll have hydroxyls on them that will allow them to self-react. This thing will react with itself because it's so long. And that alcohol group will just react with the ketone or the carbonyl group, in this case the aldehyde group. So we don't need an alcohol to be a separate molecule reacting with our aldehyde. It can be part of the same molecule, just far down the chain. When this happens, it forms a ring. It actually closes and reacts with itself, and it forms a hemiacetal. And so each one of our cyclic sugars will be hemiacetals. And then when we take our cyclic sugars and we start reacting them together, we're going to see that they'll form long chains, or they'll form disaccharides, little units of two. But once that happens, we'll be looking at acetals. We'll have an acetal linkage. And that's ultimately what we're building towards, so that you can understand the naming conventions when we look at carbohydrates. But here it is again, this one with glucose. You can see glucose here. The number 5 carbon on glucose has an OH, so the alcohol group. The number 1 carbon has the aldehyde group. That will form a ring. It'll autocyclize, and we get the hemiacetal of glucose, the ring structure of glucose, where the number 1 carbon has an OH group and also an alkoxy group. And then when we form a bond, that number 1 carbon will have an alkoxy group this way, and then the next sugar will be the other alkoxy group. So that's how we'll link some sugars together. Now what's neat is that an alcohol can actually add to a cyclic hemiacetal to form a cyclic acetal. So this is a kind of a preview of what we're going to see with sugars. Imagine taking 2 cyclic acetals and reacting them together. That's what we'll see next chapter. But as a sort of simplified version of that, if we take our ring glucose and we just add like a simple alcohol to it, you can see how that's going to form an acetal. So where we have our OR group going in this direction, and then our other OR group is just a short chain, alcohol. When we start linking sugars together, like I mentioned, instead of using a short chain alcohol, it'll just be another cyclic hemiacetal, and those will just link together to form cyclic acetals like this. So imagine instead of adding another small alcohol, we added another cyclic hemiacetal. And one of those OH groups will be the alcohol group, and it'll react with our number 1 carbon, with our hemi, to form an acetal. So we're going to be building towards that. We'll look at that next chapter. All right. So identifying what a cyclic, I'm sorry, identifying an acetal, identifying a hemiacetal, that's the objective here. And then being able to show these reactions or to see a reaction and to predict what the product might be would be the next step. So go ahead and try to identify these as acetal or hemi. Shouldn't be too hard. If there's an OH on it, then it's a hemi. If it's ORs, then it's an acetal. See if you can do this. Draw the condensed structural formula for the acetal formed by adding CH3OH or methanol to butanal. 2, 3, 4. Butanal plus methanol. So first off, right, this is going to be a hemiacetal. We're going to get a hemiacetal. So we'll have to do 2 rounds of this. So once you get your hemi, then you'll add your second alcohol. That, or if you already know what the acetal should look like, remember, this won't change. This won't change. One of these bonds breaks, so that we have 2. Both of them will have O's on them, and then whatever is attached to those alcohols. Just takes a little bit of practice, okay? But I really recommend that you do some more practice. There is some in the homework, and there's also some in the back of the book, but give those a shot. I don't think I included a concept map on this one, so I apologize for that. But it would look something like aldehydes and ketones. You know, aldehydes can go into carboxylic acids or go back into primary alcohols. It would have secondary alcohols, ketones, no oxidizing. You would be able to see that aldehydes and ketones can go into hemi and then into acetal by adding alcohols. You would be able to see that aldehydes can be actually, this we don't have to say anything about reduction here because it's just the reverse of the oxidation. So it can be reduced with hydrogen gas back into, right? Carboxylic acids can be reduced back into aldehydes, which can be reduced back into alcohols, primary, and then ketones can be reduced back into secondary alcohols. We talked about Tolin's test and Benedict's test, but both of those were oxidations. Tolin's will separate an aldehyde from a ketone. Benedict's will find an aldehyde that has a neighboring hydroxyl group. All right, guys. See you in the next one. Take care.